Chapter 10 is about electromagnetism, and the focus of our discussion today is more on problem solving. We will be solving problems on magnetic field, magnetic force, and some basic problems about electromagnetic waves. The needle of a compass is a permanent magnet in which it has two poles, the North Pole and South Pole. The behavior of a magnetic pole is the same with the behavior of an electric charge. So in electric charge, like charges repel, unlike charges attract. The same thing with magnetic poles, unlike poles attract, like poles repel. Surrounding a magnet, there's a magnetic field. So that's a region of space in which there's a effect of the magnetic force. The magnetic field lines and patterns of iron filings in the vicinity of a bar magnet and the magnetic field lines in the gap of a horseshoe magnet can be illustrated in the diagram, in which, as you can see, the direction of magnetic field is from the South Pole going to the North Pole. We already discussed in the previous chapter that when a charge is placed in an electric field, it experiences a force according to this formula, in which electric force is equal to the charge multiplied by electric field. So we computed for electric field, in which in that case electric field can be computed using the formula electric force divided by the test charge, or simply charge, in which force can be expressed in Newton, charge is in Coulomb, and electric field will be in Newton per Coulomb. The following conditions must be met for a charge to experience a magnetic force when placed in a magnetic field. So the charge must be moving. Then the second, the velocity of the charge must have a component that is perpendicular to the direction of the magnetic field. In finding the direction of the magnetic field, we're going to use the right-hand rule number 1. So in the right-hand rule number 1, we just need to extend the right hand so the fingers point along the direction of the magnetic field and the thumbs points along the velocity of the charge. So the palm of the hand then faces in the direction of the magnetic force that acts on the positive charge. If the moving charge is negative, the direction of the force is opposite to the predicted right-hand rule number 1. For us to compute for the magnetic field, so we have this formula: B is equal to F, which is the magnetic force, divided by the test charge, multiplied by B, which is the speed of the charge or velocity of charge, multiplied by the sine theta, where the angle theta is 0, or the theta is between 0 to 180 degrees. So that's the angle between the velocity of the charge and the direction of the magnetic field. So in this formula, we can get the unit for magnetic field, in which that is equal to Tesla. So in 1 Gauss, so that is equal to 10 to the negative 4 Tesla. Again, for us to get the Tesla, so that is simply Newton all over Coulomb multiplied by meter per second multiplied by sine theta. So Newton per Coulomb divided by meter per second, so that's equivalent to Tesla, or that is simply Newton second divided by Coulomb meter. So here's an example about magnetic force. So we're going to use here the formula for magnetic force, which is test charge multiplied by the speed of the charge multiplied by the magnetic field multiplied by sine theta. So we have Q naught V as in victory, magnetic field, sine theta. In this problem, so we have the given particle, which is a proton. It has a speed of 5.0 times 10 to the 6 meter per second. So the given speed here is 5 times 10 to the 6 meter per second. So we already have the value for V. So that's the value, or the magnitude of the value. So the proton encounters a magnetic field whose magnitude is 0.40 Tesla. So the magnetic field here is also given, so that's 0.40 Tesla. And the direction, it makes an angle at an angle of 30 degrees with respect to the proton's velocity. So we also have the given theta, which is 30 degrees. So the first question is, find the magnitude and direction of the force on the proton, and B, the acceleration of the proton, and C, what would be the force and acceleration of the particle if this is an electron. For us to solve letter A, so for us to get the magnitude and direction of the force on the proton, of course we need to use this formula. So that's equal to, force is equal to charge multiplied by velocity, then magnetic field multiplied by sine theta. In the given particle here is a proton, and we know that the charge of a proton is positive 1.60 times 10 to the negative 19 coulomb. Again, the difference between the charge of electron and proton is just the sign. For electron, we use negative 1.6 times 10 to the negative 19 coulomb. So they have the same magnitude, but they have different charge. Again, proton is a positively charged, then an electron is a negatively charged particle. So the charge of proton is 1.60 times 10 to the negative 19 coulomb. We have the given velocity. Velocity is 5 times 10 to the 6 meter per second. And then the magnetic field is 0.40 Tesla. We have the given angle between the angle with respect to the proton's velocity, and that is 30 degrees. So we have sine 30 degrees. So just multiply all the given quantities. So the answer is 1.60 times 10 to the negative 13 Newton. To solve for letter B, so we have the formula for the second law of motion, in which for the second law of motion we have this equation. So force is equal to mass multiplied by acceleration. So in this case, we're going to treat the particle as a proton, because the particle here is a proton. So we need to consider the mass of the proton, which is equal to 1.67 times 10 to the negative 27 kilogram. So here the question is to find the acceleration of the proton. So acceleration is simply force divided by mass. So the force here is the computed magnetic force, and mass is of course the mass of proton. So based on the computed magnetic force, so that's equal to 1.60 times 10 to the negative 13 newtons. So divided by the mass of the proton, which is constant, so that's equal to 1.67 times 10 to the negative 27 kilogram. So the acceleration here is equal to 9.6 times 10 to the 13 meter per second squared. For letter C, what would be the force and acceleration of the particle if the particle is an electron? So we just need to replace a proton by an electron. So since they have the same magnitude of charge, that is also 1.60 times 10 to the negative 19 coulomb, we will get the same value of magnetic force, which is 1.6 times 10 to the negative 13 newton. The difference here is the mass of electrons. So mass of electron is also constant, that is equal to 9.11 times 10 to the negative 31 kilogram. So force or magnetic force divided by mass of electron, so that's equal to 1.8 times 10 to the 17 meter per second squared. So this is the acceleration of the proton and also the force of the proton. So illustrated here is the difference between the movement of a charge in an electric field and in a magnetic field. So because of the effect of magnetic field, there will be change in the direction of the charge, as shown in the diagram. So we have another formula to get the magnetic field or the magnetic force, so that is in terms of this formula. So this is derived from our formula a while ago, which is QB sine theta. So we just divide or multiply this equation by delta t over delta t. We all know that delta t over delta t is simply 1. So it's just like we are multiplying the whole equation by 1. So given this equation, so that will become change in charge divided by change in time. In our topic in electrostatic and also in electric circuits, we computed for current. So current is simply the change in charge over the change in time. So meaning this equation is equal to current. And then the speed of the speed of the particle or of the charge multiplied by the change in time. So that is simply speed multiplied by time. In the formula for motion, that is equal to distance or L. Again, v multiplied by time is equal to distance or L. So we have this L. So therefore, we can replace delta Q, delta T, b delta T by these variables or these quantities. We have I multiplied by L, and then we just need to copy the formula b sine theta. Again, to compute for the magnetic force, that is equal to I, which is current. L is the length or wire length, B is the magnetic field, and sine theta is of course the given angle. Here's an example about the force and acceleration in a loudspeaker. So here we are asked to get the magnetic force that acts on the coil and the cone. And then for the second problem or the second question, find their acceleration. So we need to identify all the given here. So we have the given diameter of the speaker that is equal to 0.0025 meter. It contains 55 turns of wire. So the number of turns is also given. And that is placed in 0.10 Tesla magnetic field. Magnetic field is also given. So the current in the voice coil is 2 amperes. Current is also given. So determine the magnetic force. Again, we're going to use this formula to get the magnetic force. Current is 2 ampere. So that's equal to 2 ampere. L can be computed by multiplying the number of turns with pi and then multiplied by the diameter. So here's the formula. Okay, so that's diameter multiplied by pi multiplied by the number of turns. So that's how to get the L, or the length of the wire. And then Tesla is given, or the volume of magnetic field is given, so that's equal to 0.10 Tesla. And then of course the angle between the magnetic field and the velocity is 90 degrees, so that's equal to sine 90 degrees. So 2.0 ampere multiplied by 55 pi multiplied by 0.0025 meter multiplied by the given magnetic field 0.10 Tesla, then sine 90 degrees. The volume of the magnetic force here is 0.86 newtons. Again, to solve for letter B, we just need to use the formula for the second law of motion, which is acceleration is equal to force divided by mass. Again here, the mass here is given, so that's 0.02 kilograms. And then of course we have the computed value of the magnetic force, 0.86 newton. So just divide 0.86 newton by 0.020 kilograms. So the acceleration of the charge here is equal to 43 meter per second squared. Okay, so this is how to compute for net torque. Okay, but basically the formula for net torque is equal to NIA B sine theta, in which NIA is the magnetic moment, B is magnetic field, and of course sine theta is the given angle. For us to compute for the number of turns of wire, again, so we have this the formula on the previous slides, and then usually the number of turns of wire is given. The A here is the area, N is the number of turns, and of course I is the value of the current. So a coil of wire has an area of 2.0 times 10 to the negative 4 meters square. So we have the given area. So here's the area. It consists of 100 loops of turns. The number of turns is given. So that's 100. The number of turns is given. And then we also have the current, which is 0.045 ampere. Current is 0.45 ampere. And of course, again, we have the value of the area. That's 2 times 10 to the negative 4 meters square. So from this given, we can compute the magnetic moment of the coil, and the magnetic moment is simply NIA. So that's the formula. So the value is equal to 9 times 10 to the negative 4 ampere meter square. Find the maximum torque that the magnetic field can exert on the coil. So we're going to use this formula, so that's equal to magnetic moment multiplied by magnetic field and then sine angle. So NIE is already computed, so that's 9 times 10 to the negative 4 ampere meter square. Magnetic field is 0.15 Tesla. This 0.15 Tesla. And sine angle is the perpendicular, so since they are perpendicular to each other, we're going to use sine 90 degrees. So that's sine 90 degrees, which is equal to 1.40 times 10 to the negative 4 Newton meters. So this is the value of the torque based on all the given. We can also compute the magnetic field along a straight wire. So this is the straight wire, in which, as you can see, here's the magnetic field, in which we can find the magnetic field based on the radius. So the formula to get the magnetic field is simply mu naught multiplied by I divided by 2 pi r, in which mu naught is constant, that is the permeability of free space. So the value of that is 4 pi times 10 to the negative 7 Tesla meter per ampere. 4 pi times 10 to the negative 7 is also 12.0 4.57 times 10 to the negative 7. Okay, so if you want to use your calculator, you can use 4 pi times 10 to the negative 7 or simply 12.57 times 10 to the negative 7. Again, for us to solve the magnetic field along a straight wire, the formula is magnetic field, or B, is equal to permeability of free space, which is constant, multiplied by the given current divided by 2 pi r. Again, r here is the radius of the magnetic field based on the illustration. The magnetic field strength at the distance of 6 centimeters from a thin straight wire is 0.0004 Tesla. So what is the current in the wire? So we need to identify the given here. We have the given distance, the magnetic field strength at a distance. So the distance from the magnetic field strength is 6 centimeters. So R is equal to 0.06 meter, or equal to 6 centimeters. We have Tesla, which is magnetic field, so 0.00004 Tesla. So we need to compute here for the current. So based on the formula for magnetic field, so magnetic field is equal to mu naught multiplied by I over 2 pi r. So we need to solve for current. So current is equal to magnetic field multiplied by 2 pi r divided by permeability of free space. So this is equal to magnetic field is 0.00004 Tesla multiplied by 2 pi and then multiplied by the given distance, or r, that's equal to 0.06 meter, and that is to be divided by the value of the permeability of free space, that is 4 pi times 10 to the negative 7 Tesla meter per ampere. So the value here is equal to 12.0 ampere. So here's the value of the current. So in this problem we are looking for this problem, so this is also about magnetic field in a infinitely long straight wire, in which according to the problem we have the given current. So current is equal to 12.0 ampere. At a distance r from the wire, the magnetic field is 2.5 times 10 to the negative 5 Tesla. So we are asked to compute for the value of r in meter. So that's the distance. So to derive the formula, so R is simply permeability multiplied by current divided by 2 pi multiplied by magnetic field. So this is the formula to get the distance. So R is equal to, so permeability is constant, so 4 pi times 10 to the negative 7. The current is given, 12.0 ampere, divide by 2 pi, and then of course the value of the magnetic field, 2.5 times 10 to the negative 5 Tesla. Here the value of R is equal to 0.096, or that is equal to 0.10 meter. So the distance is equal to 0.10 meter. So current exerts a magnetic force on a moving charge. So still, this is an example about a long straight wire. It carries a current of 3 amperes. A particle has a charge of 6.5 times 10 to the negative 6 coulomb and is moving parallel to the wire at a distance of 0.050 meter. So the speed of the particle is 280 meter per second. So the question here is, what is the magnitude and direction of the magnetic force on the particle? Again, the formula to get the magnetic force is this one, in which that is equal to charge multiplied by speed multiplied by magnetic field, then sine theta. Again, the angle here is equal to 90 degrees. So, and also, the formula for magnetic field for a long straight wire, we used that a while ago in the previous slide. So that's equal to mu naught multiplied by I divided by 2 pi r. So we're going to use this formula for the magnetic field. So let's compute for the magnitude and direction of the magnetic force. So that's equal to, so charge is 6.5 times 10 to the negative 6 coulomb. So we have 6.5 times 10 to the negative 6 coulomb, and then multiplied by Speed is 280 meter per second, and then multiplied by the magnetic field. Magnetic field is permeability, which is 4 pi. So this is 4 pi times 10 to the negative 7. Okay, Tesla meter per ampere. And then multiplied by current. So current here is 3 amperes. 3.0 amperes. And then sine 90 degrees is equal to 1 divided by 2 pi multiplied by the distance. The distance here is 0.050 meters. So here the answer is 2.18 times 10 to the negative 8 newtons. So here is the answer. And of course, the direction can be identified using the right hand rule. Again, so this is the formula how to get the magnetic field. So this is the formula we use to solve the problem. And then, so this is the loop of wire. On the previous slides, the formula for magnetic field is mu permeability multiplied by current divided by 2 pi r. So that's applicable for the straight long wire. So if the wire is a loop, okay, so instead of using that formula, we're going to use this one. So that is the same, almost the same formula. So in this one, we're going to have the denominator, which is 2 multiplied by the radius. So we need to get the radius here. So that's the capital R. Again, in the previous slide, R there is equal to the distance, and then in this one, the capital R is the radius, since we are dealing with a circular loop. So the magnetic field at the center of a 2.5 centimeter diameter loop. So we have the given diameter loop. Okay, the diameter of the loop is 2.5 centimeters, and then the current is, or the magnetic field. So here's the magnetic field. That is equal to 0.0045 Tesla. So the question is, what is the current in the loop? Again, we're going to use the formula. So B is equal to permeability multiplied by I divided by 2R. Okay, so this is the formula in a loop of wire. We are asked to get the current. So current is simply magnetic field 2R divided by permeability. So this is magnetic field is 0.00045 Tesla multiplied by 2R. So 2R is, the R here is the radius, so 2 multiplied by the radius is diameter. So meaning this 2R can be replaced by diameter, and diameter is given. So that's 2.5 centimeters or 0.025 meter. So in this equation, guys, don't forget to convert your units. If the given unit is centimeters, so meaning you need to convert that to meter, because Tesla is as an SS system or MKS system. This is to be divided by the value of permeability, or mu naught. So that's 4 pi times 10 to the negative 7 Tesla meter over ampere. So this one is equal to 8.95 ampere. So this is an application of the magnetic concept on a loop wire, in which we have a solenoid, in which for a solenoid we can compute the magnetic field. So in a solenoid, the formula for magnetic field is permeability free space multiplied by the number of turns per unit length, or small n, multiplied by the current. Again, we're going to use this formula for a solenoid. So that's the concept about magnetic field, magnetic force. Okay, magnetic field in a long straight wire, magnetic field in a loop of wire, and then magnetic field inside a solenoid. So this is about electromagnetic waves. And again, electromagnetic waves is different from a mechanical wave. In our discussion in the previous chapter about waves and sound, so we are dealing with the mechanical waves. So we discussed transverse wave and longitudinal wave, in which sound wave is classified as a longitudinal wave. And then for transverse wave, so we can classify transverse wave as any wave in which the direction of motion is perpendicular to the direction of the vibration of the wave. So one example of that is an electromagnetic wave. And the difference between also with the electromagnetic waves and mechanical waves, for a mechanical wave, we need a medium. So meaning we need a solid, a liquid, or gas for the wave to travel. Unlike for electromagnetic waves can travel even in empty space, even without a medium. So the common example for this is light. So electromagnetic wave is a combination of transverse wave again. So this is a combination of the electric wave or electric field and magnetic field, in which they are traveling perpendicular to each other. So the direction of wave is in this direction, and the direction of vibration is also up and down. So see, this is a transverse wave. Again, electromagnetic wave is an example of a transverse wave. So the speed of electromagnetic wave in a vacuum is constant. So that is 3 times 10 to the 8 meter per second. So since light is an example of electromagnetic wave, and light has the same value, so the speed of light is also 3 times 10 to the 8 meter per second. Shown here are the different example of waves. So we have the different wavelength and the different frequency depending on the, of course, the different electromagnetic waves. And electromagnetic waves can be classified according, of course, with a wavelength and frequency. So we have the radio waves, infrared, ultraviolet, X-rays, gamma rays, and of course we have the visible light. So we can compute the speed of electromagnetic wave using this formula. So here we are using C. Usually C is equal to the speed of light, and C is constant, which is 3 times 10 to the 8 meter per second. F here is the frequency. So the frequency is the number of waves that's passed through a given point in 1 second. And then the wavelength here is the lambda. Of course, we know the wavelength, so that's the distance between 2 points in phase. And then, of course, based on this formula, we can compute for frequency of the electromagnetic wave. So that's simply C over wavelength. And then, of course, for wavelength, so that's equal to C divided by the frequency. Again, in our waves and sounds chapter mechanical waves, so the C here is equal to V, okay, in which V is the wave speed, in which wave speed can be computed by this formula also. That's wavelength multiplied by frequency. So find the range in wavelengths for visible light and the frequency range between 4 times 10 to the 14 Hz and 7.9 times 10 to the 14 Hz. So this is in terms of Hertz, meaning this is the given frequency. So we are asked to get the wavelength. So wavelength is C, or speed of electromagnetic wave, divided by the frequency given. So again, so this is equal to, C is equal to 3 times 10 to the 8 meter per second. And then we have this given frequency. So that's equal to 7.5 times 10 to the negative 7 meter, or 750 nanometers. Usually the wavelength here is expressed in terms of nanometers. But of course, for you to get the, or to convert the unit, let's be reminded that 1 nanometer is equal to 1 times 10 to the negative 9 meter. For the second one, so the given frequency is 7.9 times 10 to the negative to the 14 Hertz. Okay, again, so we have the given speed of the electromagnetic wave, and then we have the given frequency. So that's equal to 3.8 times 10 to the negative 7, or 380 nanometers. X-rays can have a wavelength of 1.2 times 10 to the negative 11. So wavelength is 1.2 times 10 to the negative 11 meter. And reach a frequency of 3.5. Frequency is 3.5 times 10 to the 19 Hertz. Based on these values, what is the speed of this X-ray? So we are asked to get the speed, or the C. Formula is wavelength multiplied by frequency. So 1.2 times 10 to the negative 11 meter multiplied by 3.5 times 10 to the 19 hertz. So the speed of X-ray is equal to 3.41. Okay, I will compute this one. So that is equal to 3.5 raised to 19 multiplied by 1.2 raised to negative 11. So the answer here is 4.2 times 10 to the 8 meter per second. So here is the speed of X-ray. So what is the frequency of visible light with wavelength of 378 nanometers? Wavelength is 378 nanometers, or 3.78 times 10 to the negative 7, or 378 times 10 to the negative 9 meters. Okay, so we are asked to get frequency. Frequency is equal to C over wavelength. So C for visible light is equal to 3 times 10 to the 8 meter per second over 3.78, or 378 times 10 to the negative 9, or 3.78 times 10 to the negative 7 meter. Frequency here is equal to 7.94 times 10 to the 14 hertz. So electromagnetic waves also can exhibit a Doppler effect, but it differs from two reasons. So this is different from sound waves because we already discussed Doppler effect, but the Doppler effect we discussed is more on sound waves, in which according to the Doppler effect we can change the frequency heard by the observer depending on the movement of the source of the sound, the movement of the observer, and also the medium. So in this case, for the Doppler effect, it differs for two reasons. Sound waves require a medium, whereas electromagnetic waves do not. So this is the difference between a mechanical wave and electromagnetic wave. For electromagnetic waves, they do not require a medium. For sound, it is the motion of relative to the motion that is important. Okay, for electromagnetic waves, only the relative motion of the source and observer is important. So we can compute the frequency here. So the frequency is equal to the frequency of the source, okay, multiplied by 1 plus or minus the relative velocity divided by c, which is constant. Example. So a radar gun of a police car emits an electromagnetic wave with a frequency of 8 times 10 to the 9 hertz. Okay, here the value of f sub o is we can get the value of f sub o here, but here we have the given frequency, which is 8 times 10 to the 9 hertz. That is the value of the frequency of the source of the electromagnetic wave. So that's equal to 8 times 10 to the 9 hertz. So this is equal to Fs. The approach is essentially head-on. So the wave from the gun reflects from the speeding car and returns to the police car, where onboard equipment measures its frequency to be greater than the emitted wave by 2100 hertz. So meaning there's a difference. The difference in the frequency, the change in frequency. So the difference in frequency is 2100 hertz. Find the speed of the car with respect to the highway. So the police car is parked, meaning the motion or the velocity of the car is at rest. So here we have two equations. So we can use these equations. So the frequency observed by speeding car, and here is the equation for the frequency observed by police car. So we just need to get the difference between the two. Okay, so that is simply f prime naught minus fs equal to, so this equation, we will be arriving on this equation. Okay, and that is, so the final formula will be this one. Okay, let's just use algebra. So we will be arriving on this final equation. So that's 2 multiplied by the frequency of the source multiplied by the relative velocity divided by the c, in which in this case we have to get the relative velocity, because we are asked to get the speed of the car with respect to the highway, so meaning we need to get this value. So just derive the formula for that one. Okay, we can have this final formula in which relative velocity is equal to F0 prime minus Fs over 2Fs multiplied by c. So the Fo prime minus Fs, so that's the difference in the frequency. And the difference in frequency is already given, so that's equal to 2100 Hz. So we have 2100 Hz divided by 2 multiplied by the frequency of the source of the electromagnetic waves, which is the given. Okay, that's 8 times 10 to the 8 Hz. So we have 2 multiplied by this, multiplied by the value of c, which is constant, so that's 3 times 10 to the 8 meter per second. So the answer here is 39 meter per second. So this is the chapter 10 of our for our subject. Thanks so much.